Good afternoon. In this video, we will be discussing classification and regression trees. In this session, we describe a flexible data-driven method that can be used for both classification called classification tree and prediction called regression tree. Among the data-driven methods, trees are the most transparent and easy to interpret. Trees are based on separating records into subgroups by creating splits on predictors, and these splits create logical rules that are transparent and easily understandable. For example, if age is less than 55 and education is greater than 12, then class is equals to 1. Or if income is greater than 92.5 and education is less than 1.5 and family is less than or equal to 2.5, then the class is 0. The resulting subgroups should be more homogeneous in terms of the outcome variable, thereby creating useful prediction or classification rules. This figure shows a tree for classifying bank customers who receive a loan offer as either acceptors or non-acceptors. Based on information such as their income, education level, and average credit card expenditure. One of the reasons that tree classifiers are very popular is that they provide easily understandable classification rules, at least if the trees are not too large. Consider the tree in this example. The gray terminal nodes are marked with 0 or 1 corresponding to the classes non-acceptor, which is 0, or acceptor, which is 1. The values above the white nodes give the splitting value on a predictor. The values below the nodes gives the number of records in the split. This tree can easily be translated into a set of rules for classifying a bank customer. For example, the bottom left rectangle node under the family circle in this tree gives us the following rule. If income is greater than or equal to 106 and education is less than 1.5 and the family is less than 2.5, then the class belongs to 0 or non-acceptor. The two key ideas underlie classification trees. The first is the idea of recursive partitioning, that is of the space of the predictor variables. The second is the idea of pruning using validation data. In the next few sections, we will show recursive partitioning and explain the pruning methodology. Here are the steps in recursive partitioning. First, we pick one of the predictor variables as x sub I and pick a value of x sub I, say s sub I, that divides the training data into two not necessarily equal portions. Measure how pure or homogeneous each of the resulting portions are. Pure here means that there contains records of mostly one class. The algorithm tries different values of x sub I and s sub I to maximize purity in initial split. And after you get a maximum purity split, repeat the process for a second split, and so on. Let's have an example using the riding mowers dataset. So this is classifying 24 households as owning or not owning riding mowers. The predictors are, or the variables are, income and lot size. So a riding mower manufacturer would like to find a way of classifying families in a city into those likely to purchase a riding mower and those not likely to buy one. A pilot random sample of 12 owners and 12 non-owners in the city is undertaken. Here is our data set for the riding mowers. There are 24 records, 12 records has ownership of owner, and 12 records are non-owners. This data shown in 9.1, if we apply the classification tree procedure to this data, the procedure will choose income for the first split with a splitting value of 60. And the x sub 1 and x sub 2 space is now divided into two rectangles, one with the income is less than 60 and the other with income greater than or equal to 60. This is illustrated in figure 9.3. We will show you how we will manually find the split. But before that, let's discuss the measuring impurity. So there are a number of ways to measure impurity. The two most popular measures are the GINI index and an entropy measure. We describe both and denote the M classes of the response variable by k equals 1, 2, and up to M. So the GINI impurity index for a rectangle A is defined by, when we say rectangle, that's the first part of the data set that is being split. So we define it to be, or the GINI impurity index is defined by the formula given in the slide, where P is the proportion of cases in rectangle A that belongs to class K. So I of A equals to 0 when all cases belong to same class. And the max value when all classes are equally represented is equals to 0.50, or no majority in a particular rectangle. The second impurity measure is the entropy measure. The entropy for a rectangle A is defined by the formula shown in this slide, where P is the proportion of cases out of M in rectangle A that belong to class K. The entropy ranges between 0, which is most pure, and log base 2 of M, which is equal representation of classes. Impurity and recursive partitioning. Obtain overall impurity measure using weighted average of individual rectangles. At each successive stage, compare this measure across all possible splits in all variables and choose the split that reduces impurity the most, and chosen split points become nodes on the tree. So let's illustrate how this is created. But take note that in a tree structure, the split points become nodes on tree, or the circles with split value in center, and the rectangles represent the leaves, the terminal points. No further splits, the classification value noted. Numbers on lines between nodes indicate the number of cases, and we read down tree to derive the rule. If, for example, or to derive the rule. For example, this is an example of the rule derived from a classification tree. If lot size is less than 19 and if income is greater than 84.75, then the class is equals to owner. So I'm going to show you how do we build the classification tree given the formulas that we showed earlier. And first, let's create the classification tree manually using Excel. So this is now our data set for the riding mowers. So we have the predictors income and the lot size and the class ownership with values non-owner and owner. So there are a total of 24 records. 12 records are for owners, and there are 12 records for owners, and there are also 12 records for non-owners. So what we do here is we will build the classification tree. First, you'll have to identify which predictor is the first node of our classification tree. So first, let's have the values of your income. Here we we put all the values of our income, and then we classify them to owners and non-owners, and then we also calculate the subtotal. The first part of owners and non-owners here is those records whose income is less than or equal to 33. Okay, so we use here the COUNTIFs formula, and we identify here, we simply count the number of owners in our data set, the number of owners in our data set whose income is less than or equal to 33. And there is no less than 33. So 0. Less than or equal to 33. And the non-owner for less than or equal to 33 is 1. For the next owner and non-owner is the greater than 33. So greater than 33, we have how many owners here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And non-owners here are 11. The total of 12 plus 11 is 23. Then we have the total number of records is 1 plus 23 is 24. So we copy the formula down, and then we compute for the GINI left, okay, of the left side. Okay, this is the left side. Then we have to compute the GINI using the formula 1 minus our number of owners divided by the subtotal of the left. Then we squared, so we have a square here, exponent 2 minus the number of non-owners minus the number of non-owners divided by the subtotal, then squared. So the GINI left here is 0. Then using the formula of entropy, we have the number of owner divided by the subtotal times the log of the owner divided by subtotal base 2 minus the number of non-owner divided by the subtotal times log number of non-owner divided by the subtotal, and the log uses the base 2. Then for the GINI right, we will be computing for the GINI of the right side of the rectangle. So we have 1 minus the number of owner divided by the subtotal of this right side. Then we have a square minus the number of non-owner divided by the subtotal and squared. Next is the entropy of the right side. So this is the GINI of the left and the entropy of the left, and the GINI of the right and the entropy of the right side. Then we get the GINI impurity, which is the subtotal divided by the total, number of records times the GINI left plus the subtotal of the right divided by the total times the GINI right. Next, we have the entropy. We have the subtotal divided by the total times the GINI or the entropy left plus the subtotal of the right divided by the total times the entropy right. So we have the following GINI measures and entropy measures. So we copy all the formula, and then we have the following. We get all the following values. For next, we also have to compute for the GINI and entropy for each of the values of the lot size. So we copy all the values of the lot size, and the same process we compute for the number of owners and non-owners in the left side and the right side with the total number of records, and the GINI left and the entropy left, the GINI right, entropy right, and the total GINI and entropy. So based on the values here, we can see that the list GINI is at this record. So this means that the first split will be income in the income. Again, this is our income values, and these are our lot size. So the list GINI that we have is from the income, and that is in this records, row 38 and 46, but we'll use the first one. So this is belonging to less than 60. So that will be our first node of the classification tree. That will be income is less than 60. And most of the ownership whose income is less than 60 is non-owners. So this is our first node. Next is we'll have to find the node in the left side of our tree and in the right side of the tree. So first we'll have to split. After getting the first node, we have to split again. So we have to split our data set. So in the next sheet, we show here that this is our data set. We only use from this data set, we only use the records here, the records whose income is less than 60, and these are highlighted in yellow. So we have to find again the next node, whether it's income or lot size, and its value. So we copy the values for the income here, 33, 43.2, 47.4, and so on. So we have this values, and the lot size are 14, 16, 16.4, 17.6, 18.8, 20.4, and 20.8, and 22. So this is how we do the classification tree manually using Excel. And then the same process here from income and lot size, we can see that the split will be from the lot size, which is less than 21. So in our tree, this is our tree now. Income is less than, if the income is less than 60, so we have this side as the yes. So under less than 60, the next split is lot size is less than 21. Next is we'll find another way to split what's the next node under lot size is equals to 21. So in the next sheet, we have this records from the previous record, and then we highlighted those whose lot size is 21. So these are the only records that we will use in computation of the GINI and entropy. As we observe here, we could see that all records are highlighted are all in one class, which is non-owner. So this means that there is no need for splitting. It means that all of the records whose lot size is less than 21 under this node are non-owners. So we don't need anymore to split the lot size is less than 21 node. So the next is we go to the right side of our root node, which is income is greater than or equal to 60. So that will be this coming from this data set. This is our original data set, and the income with greater than or equals to 60 are highlighted in yellow. So we again copy the values of the income and the lot size, and then we find their GINI and entropy. So we found out here that the next split will be lot size is less than 20. So that's in the right side of our root node. So that is lot size. So we added here lot size is less than 20. Next is we need to again find the split for lot size is less than 20. So we copy the data set for the lot size is less than 20. Data set from the previous sheet, and then this will be the lot size whose value is less than 20, highlighted in orange. So those are the only data that we will calculate for GINI and entropy. So here we find that the list GINI has the income that is less than 85. Okay, so we can now add here that the income is less than 25, and most of them are non-owners. So for consistency, we put all the non-owners to the left side of our tree. So this is income is less than 85. Most of them are non-owners. Next is we will find the right side of our lot size is less than 20 node. So again, these are our data set, and we will use only the highlighted orange, the record that is highlighted in orange, and we can see that all those lot size with greater than or equals to 20 are all owners. So we can just use it, and no need to compute for the GINI and or the entropy. So automatic that they are all owners. We have here no more nodes here. Automatic all those. This means that all the records whose income is less than 60 and the lot size is less than 20, they are all classified as owners. Next, we have to find the split for this node. So that is income is less than 85. So we'll find again those records under income is less than 85. And these are highlighted in orange. So we copy all the income values and the lot size value, and then we find their GINI and entropy. And we find that the GINI of income is less than this is 63.5, or less than 63.5 will have the will have the list GINI. However, since we want, this is most of this are for owners. We want to be consistent in our data structure that on the left side we will use the non-owners. So the condition will be income is greater than or equal to 62 for non-owners. Okay, for non-owners. This is our final classification tree using the GINI impurity measures. Now, using R, we have this code for running and plotting the classification tree with a single split. So we'll be using the rpart library and the rpart.plot to create or plot our classification tree. Then here we read the riding mowers.csv. This is our the file name of our data set, and then we store it in mower.df, and then we use the rpart to run a classification tree and define rpart control in rpart to determine the depth of the tree. So here we use the class.tree, and then we use the function rpart, and then we define the class. The outcome variable is the ownership, and then the data is from our mower.df, and we use the control for the depth of the tree. So here we use the max depth is equals to 2, and the method is class. To show the tree, we have the following script: PRP, then the name of our tree is in the class.tree, the type is 1, extra is 1, split font 1, and varlen is equals to -10, and this will be our output. This is for only one. This is to show only one a node. The first that is showing the first split, which is income is less than 60. And this will be the final split or the final tree representation after all splits. So you just have to add in your code to show the full tree. You will add a min split in the control function. Min split equals to 1. So we have another example 2, which is acceptance of personal loan. So this is universal bank data set. So the universal bank is a relatively young bank that is growing rapidly in terms of overall customer acquisition. The majority of these customers are liability customers with varying sizes of relationship with the bank. The customer base of asset customers is quite small, and the bank is interested in growing this base rapidly to bring in more loan business. In particular, it wants to explore ways of converting its liability or deposit customers to personal loan customers. A campaign the bank ran for liability customers showed a healthy conversion rate of over 9% successes. This has encouraged the retail marketing department to devise smarter campaigns with better target marketing. The goal of our analysis is to model the previous campaign's customer behavior to analyze what combination of factors make a customer more likely to accept a personal loan. This will serve as the basis for the design of a new campaign. Our predictive model will be a classification tree that is to assess the accuracy of the tree in classifying new records. We start partitioning the data into training and validation sets, and later introduce the idea of cross-validation. The bank's dataset includes data on 5,000 customers. The data include customer demographic information such as age, income, etc. Customer response to the last personal loan campaign, which is personal loan, and the customer's relationship with the bank, which is mortgage, securities account, etc. Table 9.2 shows a sample of the bank's customer database for 20 customers to illustrate the structure of the data. Among these 5,000 customers, only 480, which is 9.6%, accepted the personal loan that was offered to them in the earlier campaign. This is the script we use to build the classification tree for the loan acceptance data using the training set of 3,000 records. So first we use the library rpart and the rpart.plot. Then we use the universal bank.csv and store it in a bank.tf. Next we exclude the columns 1 and 5 from our dataset. Those are the variables ID and zip code columns, so we exclude them, and those will be excluded from the analysis. Then we have next is the partitioning, so we have to set the seed to 1, and we have the training. To create the training data set, we have to create random numbers, or we have to randomly select the records from our data set. So we do that with the use of the train.index and the sample method. Then from that we assign those randomly selected records are assigned in the new data, which is train.df, and those that were not selected in the train.df are stored in the valid.df. So that means 60% of the data set are stored in the train.df and 40% are stored in the valid.df for training and validation respectively. So the building of the classification tree is we use the default.ct and then we use the rpart method. So here we specify the personal.loan, which is our outcome variable, and then the data comes from the training data set, which is from the train.df, and the method is we have to specify here the class. Now to plot and show the tree, we use the PRP function. So we use the default.ct classification tree. Then we assign the arguments type equals 1, extra is 1, under equals true, and split that font equals 1, and varlen is equals to -10. So this is the result, decision or classification tree. From this classification tree, you can come up with decision rules. One example is if income is less than 114 and the CC average is less than 3, then the class is 0. Another example is income is greater than or equal to 114 and education is less than 1.5 and the family is less than 2.5, then the class is 0. Another example rule is if income is greater than or equal to 114 and education is less than 1.5 and the family is greater than or equal to 2.5, then the class is 1. Here is the code for creating a deeper classification tree. So we have the deeper.ct. Using the rpart method, we use the personal.loan as our outcome variable, and we assign the train.df in the data argument. The method is class, CP is 0, and mean split is 1. Then we count the number of leaves using the length method and specify deeper.ct $frame $var, then deeper.ct $frame $var equals the leaf. Then we plot the tree using the PRP method. And here is the output, which is a more deeper tree, which is a full tree for the loan acceptance data using the training set of 3,000 records. Next, we have this script for creating the confusion matrices and accuracy for the default or the small and the deeper or the full classification trees on the training and validation sets of the personal loan data. Stopping tree growth. The natural end of process is 100% purity in each leaf. This overfits the data, which end up fitting noise in the data. Overfitting leads to low predictive accuracy of new data. Past a certain point, the error rate for the validation data starts to increase. Pruning. An alternative popular solution that has proven to be more successful than stopping tree growth is pruning the full-grown tree. This is the basis of methods such as CART, developed by Bryman et al., implemented in multiple data mining software packages such as R's rpart package, SAS Enterprise Miner, CART, and MARS, and the C4.5, developed by Quinlan and implemented in packages such as IBM SPSS Modeler. In C4.5, the training data are used both for growing and pruning the tree. In CART, the innovation is to use the validation data to prune back the tree that is grown from training data. CART and CART-like procedures use validation data to prune back the tree that has deliberately been overgrown using the training data. The idea behind pruning is to recognize that a very large tree is likely to overfit the training data, and that the weakest branches, which hardly reduce the error rate, should be removed. In the mower example, the last few splits resulted in rectangles with very few points. 4 rectangles in the full tree had a single record. We can see intuitively that these last splits are likely just capturing noise in the training set rather than reflecting patterns that would occur in future data, such as the validation data. Pruning consists of successively selecting a decision node and redesignating it as a terminal node, looping off the branches, extending beyond that decision node, its subtree, and thereby reducing the size of the tree. The pruning process trades off misclassification error in the validation dataset against the number of decision nodes in the pruned tree to arrive at a tree that captures the patterns but not the noise in the training data. In Table 9.4, we see the complexity parameter table of cross-validation errors. For 8 trees of increasing depth grown on the universal data or the universal bank data, we can simply choose the tree with the lowest cross-validation error or X error. In this case, the tree in row 6 has the lowest cross-validation error. Figure 9.12 displays the pruned tree with 15 terminal nodes. This tree was pruned back from the largest three using the complexity parameter value CP, which is equals to 0.003436426, which yielded the lowest cross-validation error in Table 9.4. A further enhancement in the interest of model parsimony is to incorporate the sampling error, which might cause this minimum to vary if we had a different sample. The enhancement uses the estimated standard error of the cross-validation error, or XSTD, to prune the tree even further. We can add one standard error to the minimum X error. This is sometimes called the best pruned tree. For example, XSTD for the tree is in row 6 is 0.023858. We can choose a smaller tree by going up to the row with a cross-validation error that is larger, but still within one standard error. That is X error plus XSTD 0.16838 plus 0.023858 equals 0.192238. Here, the tree in row 4 is a smaller tree with the lowest X error in this range. The best pruned tree for the loan acceptance example is shown in figure 9.13. In this case, it coincides with the default tree in figure 9.9. The code for pruning the tree is shown in this slide. And this is the best pruned tree obtained by fitting a full tree to the training data, pruning it using the cross-validation data, and choosing the smallest tree within one standard error of the minimum X error tree. The classification trees provide easily understandable classification rules if the trees are not too large. Each terminal node is equivalent to a classification rule. Returning to the example, the rightmost terminal node in the best pruned tree gives us the rule: if income is greater than or equal to 114 and education is greater than or equal to 1.5, then the class is equals to 1. However, in many cases, the number of rules can be reduced by removing redundancies. For example, consider the rule from the second form or second from bottom leftmost terminal node in this figure. If income is less than 114 and CC average is greater than or equal to 3, and the CD that account is less than 0.5 and income is less than 92, then class is equals to 0. This rule can be simplified to: if income is less than 92 and CC average is greater than or equal to 3 and CD that account is less than 0.5, then class is equals to 0. This transparency in the process and understandability of the algorithm that leads to classifying a record as belonging to a certain class is very advantageous in settings where the final classification is not the only thing of interest. Beres and Linoff in 2000 give the example of health insurance underwriting, where the insurer is required to show that coverage denial is not based on discrimination. By showing rules that led to denial, example, income is less than $20,000 and low credit history, the company can avoid lawsuits. Compared to the output of other classifiers, such as discriminant functions, Tree-based classification rules are easily explained to managers and operating staff. Their logic is certainly far more transparent than that of weights in complex algorithms such as in neural networks. Classification trees for more than two classes. Classification trees can be used with an outcome variable that has more than two classes. In terms of measuring impurity, the two measures presented earlier, the GINI impurity index and the entropy measure, were defined for M classes and hence can be used for any number of classes. The tree itself would have the same structure, except that its terminal nodes would take one of the M class labels. The tree method can also be used for a numerical outcome variable. Regression trees for prediction operate in much the same fashion as classification trees. The outcome variable y is a numerical variable in this case, but both the principle and the procedure are the same. Many splits are attempted, and for each, we measure impurity in each branch of the resulting tree. The tree procedure then selects the split that minimizes the sum of such measures. To illustrate a regression tree, consider the example of predicting prices of Toyota Corolla automobiles. The dataset includes information on 1,000 sold Toyota Corolla cars. We use the first 1,000 cars from the dataset, Toyota Corolla.csv. The goal is to find a predictive model of price as a function of 10 predictors, including horsepower, number of doors, price, age. A regression tree for this data was built using a training set of 600 records. The best pruned tree is shown in figure 9.14. We see that from the 12 input variables, including dummies, only 3 predictors show up as useful for predicting price. Those are the age of the car, its weight, and the horsepower. 3 details differ between regression trees and classification trees: prediction, impurity measures, and evaluating performance. Predicting the outcome value for a record is performed in a fashion similar to the classification case. The predictor information is used for dropping the record down the tree until reaching a terminal node. For instance, to predict the price of a Toyota Corolla with age equals 60, horsepower equals 100, and weight equals 1,200, we drop it down the tree and reach the node that has the value $9,358. This is the price prediction for this car according to the tree. In classification trees, the value of the terminal node, which is one of the categories, is determined by the voting of the training records. In regression trees, the value of the terminal node is determined by the average outcome value of the training records that were in that terminal node. In this example, the value $9,358 is the average of the 279 cars in the training set that fall in the category of age is greater than or equal to 54. We describe 2 types of impurity measures for nodes in classification trees: the GINI index and the entropy-based measure. In both cases, the index is a function of the ratio between the categories of the records in that node. In regression trees, a typical impurity measure is the sum of the squared deviations from the mean of the terminal node. This is equivalent to the sum of the squared errors because the mean of the terminal node is exactly the prediction. Evaluating performance. Predictions are obtained by averaging the outcome values in the nodes. We therefore have the usual definition of predictions and errors. The predictive performance of regression trees can be measured in the same way that other predictive methods are evaluated. Example, in linear regression, that's the use of summary measures such as RMSE. The advantages of trees are the following. It's easy to use and understand. It produces rules that are easy to interpret and implement. Variable selection and reduction is automatic, do not require the assumptions of statistical models, and can work without extensive handling of missing data. The disadvantages are the following. It may not perform well where there is structure in the data that is not well captured by horizontal or vertical splits. Since the process deals with one variable at a time, no way to capture interactions between variables.